So we talked about deep sea diving at the very beginning of this chapter, and we'll talk about it a little bit more here. I'm not going to test you on the details of deep sea diving, but it's an illustration of the usefulness of these ideas of partial pressures. So when a diver breathes compressed air, you've got an abnormally high partial pressure of oxygen in the lungs. Because the total pressure is higher, that means the partial pressure is higher. And so then you get more oxygen in your body tissue, which is like, well, that should be a good thing, right? Oxygen's good for you. More oxygen should be better. Well, even oxygen is toxic at high enough levels. So oxygen toxicity occurs above oxygen partial pressures of 1.4 atmospheres. Too little oxygen is also bad. That's called hypoxia. Hypo means below. Hypoxia means low oxygen, oxygen starvation. That's going to happen down here around 0.1 atmospheres of oxygen. We do have a very large safe range in here of oxygen levels. When you breathe compressed air, not only do you get more oxygen, you also get more nitrogen. And nitrogen can be poisonous also. Above 4 atmospheres, you can get symptoms of nitrogen narcosis, sometimes called rapture of the deep, similar to being drunk on alcohol. So if you're diving thousands of meters or tens of meters below the surface, being drunk is probably not a good idea, right? Because you need good judgment. So at the surface where the total pressure of air is 1 atmosphere, the nitrogen's 0.78 atmospheres, the oxygen's 0.21 atmospheres. This is what our bodies are accustomed to. If you go, don't want a red pointer. There we go. If you go down to 30 meters, now the total pressure is 4 atmospheres. In order to breathe, the air that you're breathing has to be pressurized so that you can expand your lungs against the pressure of the water. Now the nitrogen is 3.12 atmospheres and the oxygen is 0.84 atmospheres. So this is getting up close to issues with nitrogen narcosis. So what do? Well, what divers do is they breathe something other than regular air that's compressed. They breathe something with different amounts of gases so that they get a more appropriate level of oxygen at the depth that they're diving. So one of those mixtures is called heliox. It's a mixture of helium and oxygen. So here in this problem, a diver breathes a heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So we've got a mole fraction of oxygen. So that's chi of O2 is equal to 0.050. No units on that. What that means is that the rest of this is helium. It's mostly helium. We want to have a partial pressure of oxygen that is good for us, 0.21 atmospheres.
Does that say IBE?
Pardon me?
The X, does that say IBE? The second next to X? The second.
No, that's helium.
Oh.
Oh, yeah, that's an HE. And so the question is, what's the total pressure? If you were to breathe this mixture at atmospheric pressure, you'd only be getting 0.05 atmospheres of oxygen, which is below the level at which you would die of hypoxia. But at a higher pressure, you're going to have a higher partial pressure of oxygen. So the relationship there is that the partial pressure of oxygen is equal to the mole fraction of oxygen times the total pressure. Here the mole fraction is 0.05. Instead of solving for PO2 though, we're solving for P total. So we're going to divide both sides by the mole fraction of oxygen. So the total pressure, in order to get a reasonable amount of oxygen, is the partial pressure that we're wanting divided by the mole fraction in the mixture. So 4.2 atmospheres. So if you breathe this heliox mixture at 4.2 atmospheres, you'll have the same concentration of oxygen in your tissues as we do just breathing at the surface. Any questions? So gases are often collected by displacement. We say it's collecting a gas over water. Yeah, you got a question? Yeah. So we often collect a gas by having it displace water from a container. See, I think I've got it. Yeah, there's the picture. Gases are hard to deal with because they're not going to stay in a beaker like liquids, right? So what we've got going on here is we've got a reaction between zinc and hydrochloric acid, which is generating hydrogen gas. And we want to collect the hydrogen gas. So as the hydrogen gas is generated, it's going to try to escape from the test tube. So we're going to direct it through this piece of tubing so that it comes out under this inverted beaker of water. When this reaction started, this was completely full of water. As the hydrogen bubbles through, the opening of the tube is here, but the bubbles are going to go up and they're going to displace the water. So what we end up with up here is our hydrogen gas that we want, but there's also water vapor. Because the water, as soon as there's any space up here, will begin evaporating. So we're going to have a mixture of water and hydrogen. And this is called collecting a gas over water. So we've got a mixture of the gas that we want and the water vapor. The partial pressure of water vapor is called the vapor pressure, and it depends only on the temperature of the water. So people have studied this, and you can look up the pressure, the partial pressure of water at any given temperature. And so then you can use that to subtract from your total pressure. So here is an example of a table. This one goes by about 5-degree increments. There are other ones that are much more precise. If you need something like this, it will be given to you. You definitely don't memorize this sort of a thing. But if I had 20 degrees and I needed to know the vapor pressure of water, the partial pressure that the water was exerting, it'd be 17.55 millimeters of mercury. So we can do problems like this. A sample of acetylene is collected over water. The total gas pressure is 738 torr. The volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Okay, so we have a mixture of gases, right? We have acetylene and we have water in the gas state. The total pressure is given as 738 torr. That equals the pressure from the acetylene plus the pressure of water, right? There are two gases, their pressures add up to the total pressure. It says that the volume is 523 milliliters. It says the temperature is 23 degrees Celsius. And it says at this temperature, the vapor pressure of water is 21 torr. So pH2O, the partial pressure of the water, is 21 torr. So I can put 21 torr in for this. So what's the partial pressure of the acetylene? 738 minus 21, right? 717? You see how I did that? I have two things, two pressures, and I know what the total pressure is. I know what one of these is, and so I can find the other one. It's actually so simple that it becomes difficult because you overthink it. If I did it with children and cookies or something, you'd come up with the answer right away. Okay, so I've got a pressure, I've got a volume, and I've got a temperature. I'm trying to find grams of acetylene. What can I find using the ideal gas law? Moles. So I can find moles. So the moles of acetylene are going to equal the pressure of the acetylene times the volume divided by R and T. So the pressure was 717 torr, but that's not a good unit. So is anyone wondering why, if we are always converting to atmospheres, do they keep measuring it in something else? Anybody wondering that? Because those other units are better for measuring. 0.94342 atmospheres.
Just assume that we're just going to use ATM?
You always have to use ATM because of the ideal gas constant. When you're using these simple gas laws, where you just have ratios and no gas constant, the only unit that has to be a certain thing is the temperature. It has to be in Kelvin. But the other units, pressure, volume, as long as they cancel out, they're fine. But ideal gas law, liter, atmospheres, moles, and Kelvin. So 0.94342 atmospheres. Volume needs to be in liters. So this is going to be 0.523 liters. Divided by R, 0.08206 liter atmospheres per mole Kelvin. And temperature needs to be in Kelvin. So 23 plus 273 gives us 296. I check my units, atmospheres cancel, liters cancel, Kelvins cancel. I'm going to end up with a number of moles. So I've got my pressure times 0.523 divided by 0.08206 divided by 296. 0.20313 moles of acetylene. So I need to convert that to grams. So I need the molar mass, right? I multiply by grams, divide by moles to get the units to work out. So acetylene is 12.01. Oops. I've got 2 carbons and 2 hydrogens. 26.036. Zero 0.52888 grams. That rounds to 0.529 grams. Any questions? Common way to make hydrogen gas in the lab is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Well, let's pull out some numbers, right? 154.4 milliliters. I've got 742 millimeters of mercury, and I've got 25 degrees Celsius. So that's a temperature. This is, dang it. This is a pressure, and this is a volume. Does the student have just hydrogen in their container? No. So this is collected over water. That tells me that this is wet hydrogen gas. There is hydrogen gas there and there's water vapor. And if I want the mass of hydrogen, I need to use just the pressure of hydrogen. I could calculate the number of moles of gas, but I can't really do a mass of total gas because I've got 2 different kinds of particles. I've got hydrogen molecules and I've got water molecules. So I want to find the partial pressure of hydrogen. So the pressure that I was given is the total pressure. So this is equal to the pressure of hydrogen plus the pressure of water. They can give me the partial pressure of water. What do? I go look it up. You can look stuff up on your phone, but most of the things you need to look up are also in your textbook. And sometimes when you look stuff up on your phone, you don't get anything super useful. Sometimes it gives you something in crazy units. So it's a good idea to get comfortable with your textbook. So collected over water. I need the water vapor pressure at 25 degrees Celsius. So I remember that was in one of these slides back here. It's this one right here. So if I look at the 25, it's 23.78 millimeters of mercury. 23.78 millimeters of mercury. 23.78 millimeters of mercury. So that's the partial pressure of water, or the vapor pressure of water, at this temperature. So then the pressure of just the hydrogen, I'm not going to squeeze it in there. I'll put it down here. The hydrogen that we want is the total, well, let's be consistent. The total minus the water vapor. So that's 742 minus 23.78. My calculator says 718.22. millimeters of mercury. Is that going to be a good unit for the ideal gas law? No. As long as we're down here, let's just convert that right away. 1 atmosphere, how many millimeters of mercury? 760. Millimeters of mercury cancel out. So I take that number and I divide by 760 and I get 0.945. 0.02 atmospheres. So if I use the partial pressure of hydrogen in the ideal gas law, then I'll get the moles of hydrogen. So N equals PV over RT. I just got my pressure. My volume is in milliliters. So I've got to convert that to liters. So one way we can do that is just 1.544. Milli stands for times 10 to the minus 3. So write times 10 to the minus 3 liters. That's not proper scientific notation, but your calculator's going to be fine with it. And it's really fast. So I'm just going to do it that way this time. Divided by ideal gas constant. And temperature needs to be in Kelvin. All my units are going to cancel out. So I've got that pressure times 154.4 times 10 to the minus 3. Unconventional, but still works. Divided by 0.08206, divided by 298. So I get 0.00596. Oh, let's straighten that out. 596.68 moles. I found a thing, but it's not the thing I need just yet. I am supposed to find mass in milligrams. How do I go from moles to grams? Molar mass. Okay, so hydrogen, what's the formula for hydrogen? Was it H or H2? It's H2, because this is one of those 7 diatomic elements, and this is one of those places where that matters. So the mass is 2.016 grams for every mole. And then I need this to be in milligrams, so I can put a conversion here. Milligrams on top. 1 milligram is 1 times 10 to the minus 3 grams. So I got my moles times 2.016 divided by 1 EE negative 3, and I get 12.029 milligrams, or 12.0 milligrams. Any questions?